Welcome to galvanic cells. We've already talked a little bit about balancing redox reactions and what redox reactions are, and now we're going to look at some of the applications. So galvanic cells. So galvanic cells or voltaic cells are what we're going to discuss here. The energy released in some spontaneous redox reaction can then be used to perform some work, some electrical kind of work. So we can light up a light bulb, we can run an iPod or an iPhone, we can run a car, something like that. But if we just mix our reactants together in a container, then the energy is released in whatever way nature prefers, not necessarily the way that we prefer. And usually the way that nature prefers is via heat. Ultimately, all energy goes to heat anyways. And so in order for us to actually do some meaningful work with the energy that's released in the with this spontaneous reaction, we have to separate our reactants so that we're forcing nature to do the sort of to push the energy through the way that we want it to go. So this is where we get to voltaic cells or galvanic cells. These are devices in which electron transfer occurs via some external circuit through a wire and presumably some load that we're trying to push electricity through. So voltaic cells utilize these spontaneous reactions that we talk about, these spontaneous redox reactions. So let's look at an example. If we have a strip of zinc that's placed in a solution of copper sulfate, then the copper is deposited on the zinc, and the zinc dissolves and forms the zinc 2+ ion. So here's our chemical reaction. We have the zinc solid with an oxidation state initially of 0, the copper with an oxidation state of 2+. Those react together, the electrons leave the zinc, go to the copper, and so the zinc ends up with a 2+ charge, the copper ends up with 0 charge, and so then the zinc is oxidized, this happens spontaneously, to zinc 2 by our copper 2+, and our copper 2+ is spontaneously reduced then to copper 0 by our zinc 0. And again, this entire process is spontaneous, which means if we mix these two together in a beaker, the reaction will go. We don't have to force the reaction to go with any work. So let's break this reaction down into half cells. So a half cell is each of the two compartments of a voltaic cell, and a voltaic cell consists of an oxidation half reaction and a reduction half reaction. So basically we're taking the reaction, the complete reaction, like the one that I showed on the last slide, and breaking it apart into two different half reactions that are each focusing on just basically a single element. So one involving the copper and one involving the zinc. For our oxidation half reaction, we've got our zinc 0 going to zinc 2, and we get 2 electrons out. And the oxidation is taking place at the anode. Remember, anode is similar to anion. So the anode is one that is getting the electrons. That's the one that's negatively charged. Then the reduction is occurring with the copper. So the copper 2+ is gaining 2 electrons. So this must be the reduction process to become copper 0. And the reduction takes place at the cathode. Remember, cathode is similar to cation. Cations are positively charged. The cathode will be positively charged. The electrons are leaving the cathode and going into the ion here. And so electrons are moving from the cathode to our copper. In this case, the electrons are moving from the zinc to the anode, going through the external circuit, and then going to the cathode. So we need to use a salt bridge to complete the electrical circuit. And with the salt bridge, cations are moving from the anode to the cathode, and anions are moving from the cathode to the anode. So we're using the salt bridge to balance out the charges, because if all we're doing is moving electrons from one spot, so if we've separated our reactants into 2 separate beakers, and we are moving electrons from one beaker to the other, then eventually one beaker becomes positively charged, the other beaker becomes negatively charged. We need a way of balancing that out, and the salt bridge is the way that we do that. So we have some salt. In principle, something like sodium chloride would work, although usually we use something more like potassium nitrate. So in this case, we need the potassium to move towards the negatively charged side where the electrons are moving. We need the nitrate, the negative ion, the anion, to move to the other side, the positively charged side, the side that is losing the electrons. And this will balance out the charge transfer of moving the electrons from one side to the other. So our two solid metals that we have in our beakers are called the electrodes. One of them is the cathode and one of them is the anode. And as oxidation occurs, then the zinc is converted to zinc 2 plus, and 2 electrons come out. Those electrons are then flowing towards the cathode, where they're then used in our reduction reaction with the copper. And we expect the zinc electrode to slowly lose mass, and the copper electrode to slowly gain mass. Note that the mass is still conserved, but the electrode is losing mass. Those zinc atoms with a 0 charge are losing electrons. They're going off into solution, which means individual atoms are leaving as ions as they enter the solution. So the electrode, the zinc electrode, is becoming less massive because its mass is streaming out into the solution. On the other hand, the copper electrode is gaining mass because we have copper ions in solution that are electroplating onto the outside of our copper electrode. So electrons are then flowing from the anode, the negatively charged electrode, to the cathode, the positively charged electrode. And this makes sense because electrons are going to be repelled from the negative charge and attracted to the positive charge. So again, the anode is negatively charged, the cathode is positively charged, so the electrons are moving from the anode to the cathode. So electrons can't flow through our solution. They have to go through some external wire. And our anions and cations are moving through some porous barrier or salt bridge. This is what we're calling a salt bridge. We're allowing the anions and cations to move back and forth. If we allow our reactants to move back and forth, then the reaction just occurs directly between the two reactants, and so we need to keep our reactants separated. So our salt bridge or our porous barrier needs to be semi-permeable. It needs to be permeable to some cations and anions, but not permeable to our reactants. So cations are then moving into the cathodic compartment, the compartment that contains the cathode, in order to neutralize the excess of negatively charged ions. And again, at the cathode, copper 2 is gaining electrons to become copper 0, and so the counter ion of copper 2 plus, that anion, is in excess. So we need positively charged cations to be moving from the compartment containing the anode into the compartment containing the cathode in order to balance out those electrons that are going in there. And then, on the other hand, the anions are moving into the anodic compartment in order to neutralize the excess zinc 2 plus ions that are formed by oxidation. So the zinc 2 plus ions basically need a counter ion along with them. That counter ion has to come from the other compartment, or really via the salt bridge. Let's take a molecular view of our electrode process here, and so we'll come up with some rules for voltaic cells. At the anode, electrons are products, and oxidation is occurring. At the cathode, electrons are reagents or reactants, and reduction is occurring. Then our flow of electrons from anode to cathode requires an external wire. Right? We need a wire for an external circuit, otherwise we're just generating heat with our reaction. Then our transfer of ions through a salt bridge maintains the overall charge balance for our two compartments. Otherwise, the reaction will just stop fairly shortly after it begins, once we build up a charge difference between our two sides. And this brings us to cell notation. So we want a way of describing a voltaic or galvanic cell without having to write out a really large reaction specifying exactly what is going on. So we use cell notation. This is a shorthand way of expressing the reaction that's occurring in some electrochemical cell. And the two half cells are separated by 2 bars. This represents our salt bridge. And the solid or liquid or aqueous phases within a half cell are separated by a single bar. So a single bar represents a phase change, a place where we have a phase interface between solid and liquid, between a pure liquid and an aqueous phase, between a liquid phase and a gas phase, something like that. Any of those phase interfaces are represented by a single bar. The salt bridge is represented by a double bar. So the phase and concentration for dissolved species, are written in parentheses after each species that we have. And so for our copper-zinc cell that we've discussed earlier, the cell notation looks something like this. So we have zinc solid, and then a phase barrier, a phase interface there between the solid and the aqueous phase. We've got zinc, 2+ ions aqueous. There obviously has to be some counter ion around, but because the counter ion is not involved in the reaction, it doesn't matter, provided that it doesn't precipitate with the zinc. Then we've got our salt bridge, and in the other compartment we have our copper 2+ in aqueous phase, and again some counter ion that we don't need to write. And then we've got a phase barrier there, and our copper solid. And so if we had then a zinc concentration, a zinc ion concentration of 0.1 molar and a copper ion concentration of 0.5 molar, then we would write in the concentrations that we have. So we've added in this part for the concentration of our zinc, and we've added in this part for the concentration of our copper. So within our half cell, then the cell notation is read from the left to right, with reactants on the left and products on the right. So here we have the zinc half cell, and we have zinc solid is going to zinc 2+. If we're going from a charge of 0 to a charge of 2+, we must be removing electrons from our zinc, and that means that our half reaction for that left side is going from the zinc metal to the zinc ion, so from zinc metal to zinc ion, solid to the aqueous ion, and then we have to be producing 2 electrons. And on the copper side, we have copper 2+ going to copper 0, so we have to be adding 2 electrons, and so there we have our reduction half reaction, and this was our oxidation half reaction. So this way is a little bit shorter than writing out both of those reactions. So you should be able to get from the cell notation to our half reactions. You should be able to get from the half reactions to the cell notation. You should be able to get from the half reactions to the complete reaction, or from the complete reaction to the half reactions. So that was galvanic cells.